Welcome back, everyone. I am seriously so excited about today's explainer, mostly because we're looking at something that literally affects every single one of us every single day, yet it's completely invisible. We are diving into how artificial intelligence is fundamentally rewiring our mobile networks. Seriously, we're moving from a world where humans write the rigid rules of our communications infrastructure straight into a world where AI ecosystems just run the show.
It's kind of a wild concept, right? Hooking up a system that manages billions of devices and just letting it make its own decisions. How does a network actually think for itself? Well, when you consider the sheer chaotic traffic of modern 5G and upcoming 6G data demands, traditional human-coded rules just can't keep up anymore. The environment is way too fast, way too complex, and honestly entirely too unpredictable. To wrap our heads around the scale of the problem, think of our wireless network like a massive, sprawling city dealing with a permanent, constantly shifting traffic jam. On one hand, you've got latency-sensitive data. Think real-time police surveillance video or data from autonomous vehicles. This is basically the ambulance in our city, right? It needs a high-speed, zero-interruption lane. But on the other hand, you have latency-tolerant traffic. Things like scrolling through social media or downloading a podcast. That kind of traffic can totally wait an extra millisecond or two just so your download doesn't suddenly interrupt the ambulance's critical data feed. But here's the catch. Managing that perfect balance every single microsecond, that's a superhuman task.
So let's dive into how we actually solve this. The foundation making this entire AI takeover possible is called ORAN, or Open Radio Access Network. Back in the day, network hardware was basically a locked, proprietary black box. But ORAN, it changes the game entirely. It's this disaggregated, highly flexible architecture with truly open interfaces. It basically builds an open road infrastructure that makes it entirely possible to replace those rigid, hard-coded telecom rules with dynamic, AI-driven routing.
Take a look at how the network gets physically sliced up here. Up at the top, you've got those latency-sensitive cameras, and down at the bottom are the latency-tolerant smartphones. The ORAN architecture takes these completely distinct data streams and intelligently routes them through specific radio and distributed units, the ORUs and VODUs. This whole setup creates the absolute perfect playground for an AI to step in and play traffic cop.
Okay, so how do we actually build that smart traffic cop? Well, we start at level 1, using deep reinforcement learning, or DRL. In this first approach, we essentially drop a single, incredibly smart AI agent right at the main intersection of our network. It observes everything happening, makes a resource allocation decision, and then gets a mathematical reward based on how well it did. Specifically, we're talking about rewarding it for minimizing power consumption while keeping that critical latency super low.
But that begs the question, which AI personality actually makes the best cop? Researchers decided to pit two top candidates against each other. First up, we have PPO, which is an on-policy model. PPO is, well, steady. It learns directly from its current actions and carefully stabilizes its policy updates. Then, stepping into the ring as the challenger, we have ACOR, an off-policy model. ACR is a bit more aggressive. It learns rapidly by digging through a buffer of past memories, essentially reusing old experiences to get smart really fast.
When they were actually put to the test, the results were pretty fascinating. Follow the green line there, which is our memory digger, Acer. Because of its off-policy approach, it rockets up the learning curve way faster right out of the gate. But wait, look at the red line, PPO. It starts off a bit slower, sure, but ultimately, it reaches a much higher, far more stable level of overall performance or reward. Turns out, PPO just handles the ongoing, constantly changing traffic a lot better over the long haul.
So the crucial takeaway is really driven home right here. PPO definitively wins this round. Looking at the trade-off between the energy the servers consume and the delay users actually experience, both AIs absolutely crush the old traditional greedy algorithms. But PPO, that red line down at the bottom, it finds the absolute perfect balance. It keeps the ORAN server's power consumption super low without ever letting those critical police surveillance videos lag. It's exactly what we need. All right, let's move on to the next challenge and see how this all scales up. We've got a great traffic cop now. But here is the fatal limitation of level 1. A single traffic cop, no matter how much of a genius they are, simply cannot manage an entire global metropolis. A single agent will get utterly overwhelmed by the sheer, chaotic scale of a sprawling network. Honestly, we'd be forcing one brain to do the work of thousands. So we have to level up to multi-agent systems, or MAS. We need a whole team of AI agents working together, distributing that massive workload. Check out how our new multi-agent team is mapped out across these different control loops. You've got local AI agents stationed at the ODU level making real-time split-second decisions. We're talking under 10 milliseconds here. Then, moving up, you have agents at the near-RT RIC layer looking at the slightly bigger picture, maybe every second or so. And finally, right at the top, the non-RT RIC layer handles the grand global strategy over much longer periods. It's literally an entire hierarchy of intelligence working in sync.
But here's where it gets crazy. Deploying a team introduces a truly wild physical constraint into the mix. Because these different AI team members have to constantly share data to collaborate, the actual physical distance between their servers is strictly limited by the size of their AI feedback. If that AI payload gets too large, the time it takes light itself to travel through the fiber optic cables actually becomes a bottleneck. Just think about that for a second. The smarter and more chatty our AI team gets, the closer together their physical servers actually have to be built, just to maintain real-time performance. Mind-blowing, right?
And now we reach our final boss. We have our team. They're communicating perfectly, but the wireless environment is just incredibly chaotic. People move around, storms hit out of nowhere, massive crowds gather for a concert. In all this chaos, standard deep reinforcement learning agents actually start to fail. They suffer from what's called the overfitting problem. Basically, they memorize past traffic patterns perfectly, but when a totally new, unexpected situation pops up, the AI absolutely panics. Its learning curve is just way too sharp, too rigid to adapt on the fly. So, to beat this final boss, researchers designed this ultimate setup, a multi-agent soft actor-critic architecture. Look at how it's structured. You have local distributed units acting as the on-the-ground traffic cops. Those are our actors in red, green, and blue. But up top, sitting in the regional cloud, you have a central application acting as the global critic. This critic basically oversees the actors, grading their performance and sending crucial feedback down the line to keep everyone perfectly coordinated.
But even with the critic keeping an eye on things, we still need to stop those actors from panicking every time the environment changes. Enter our final level-up tool, SAM, or Sharpness-Aware Minimization. SAM is this brilliant mathematical technique. Instead of just frantically trying to find the absolute lowest error rate on past data, which is exactly what causes that rigid overfitting, SAM actively smooths out the AI's learning landscape. It intentionally finds a comfortable, wide valley of good performance, ensuring the AI doesn't get completely stuck or derailed by extreme temporary spikes in network traffic.
Here's the rub, though. Applying SAM to every single agent all the time, that totally wastes computing power. So researchers went a step further and created Task-Aware SAM, or TA-SAM. Think of TA-SAM like an elite supervisor. It constantly measures the TD error variance, which honestly is just a fancy, highly technical way of saying it measures exactly how confused an agent is. TA-SAM pinpoints specifically which local AI agents are struggling with complex, changing environments, and then it applies that smoothing SAM math only to them. It dynamically adjusts how they explore new solutions without bogging down the rest of the network.
So it all sounds great in theory, but does all this incredible math and architecture actually work? Yeah, it absolutely does. When you deploy this highly advanced, self-correcting, multi-agent AI team using Task-Aware SAM, it boosts resource allocation efficiency and overall quality of service by a massive 22% compared to standard AI approaches. To put that into perspective, for you and me, that massive leap translates directly to fewer dropped connections, faster downloads, and perfectly seamless data, even if you're standing in a packed stadium with 80,000 other people.
The researchers behind this technology really put it perfectly. They noted that the increasing complexity of mobile networks is basically reaching the absolute limits of those old model-based optimization approaches. We are officially leaving behind the era of brittle, human-designed telecom rules. The sheer complexity of what we are building today absolutely necessitates these dynamic, data-driven, team-based AI ecosystems. They are rapidly becoming the invisible, highly intelligent operators of our entire digital infrastructure. Which really leads us to a pretty profound thought to end on today. If these multi-agent AI systems can autonomously optimize the infrastructure of our communications, literally correcting their own errors and adapting to absolute chaos on the fly, what happens when the network becomes entirely self-driving? We are standing right on the edge of a future where global networks heal, grow, and adapt entirely on their own. Thank you so much for joining me on this explainer, and as always, keep your curiosity fired up.